Classroom teaching is a high-speed collision of social dynamics, cognitive processing, and physical space. Teachers make thousands of contingent decisions a day, creating an environment that is notoriously difficult to quantify. To evaluate what actually works, educational researchers have to find a way to translate that real-time chaos into structured, objective data. This chart shows a primary data matrix built from observer ratings of 3 elementary mathematics lessons. It maps consensus scores across a framework of instructional subdimensions. By isolating the plotted paths, you see extreme variance between the green, yellow, and blue teaching profiles. We are going to reverse engineer these specific profiles by deconstructing the theory underlying this chart, a model known as the 3 basic dimensions of teaching quality. We will trace the psychological roots of these dimensions and examine the statistical gap between observing a good lesson and actually predicting student outcomes. Effectively quantifying teaching requires moving past our subjective impressions and carefully decomposing instruction into completely isolated, measurable theoretical axes. The 3 basic dimensions framework is a generic, cross-subject model that posits 3 core goals of teaching. We can map them by building a coordinate space. The first axis is classroom management. The psychological mechanism driving this dimension is maximizing time on task. Teachers use clear routines and continuous monitoring to transition allocated class time into realized learning time. The second axis is student support. This dimension targets socio-emotional requirements based directly on self-determination theory. It measures how effectively the teachers support student competence, grants autonomy, and builds social relatedness. Management secures an efficient environment, while support secures motivation. Together, they establish the foundational baseline for a functioning classroom. But students can be perfectly attentive and emotionally secure without engaging with the material. Neither of these dimensions inherently guarantees that deep intellectual understanding is taking place. That requires the third axis to complete the instructional space: cognitive activation. The psychological root of this dimension is constructivist learning theory. It differentiates cognitive activity from mere behavioral activity. A student filling out a rote worksheet is behaviorally active, but cognitive activation demands higher-order thinking and productive struggle. Observers look for operational markers. Do they explore prior knowledge? Do they utilize Socratic discourse? Are the tasks strictly challenging? The ultimate goal is for students to build flexible, interconnected ideas, what psychologists call intelligent knowledge, rather than relying on rote memorization. Across empirical studies, researchers identify cognitive activation as the most difficult dimension for teachers to execute. It acts as the actual engine of knowledge construction, but it is wholly dependent on the environment established by the first 2 dimensions. We can map these 3 theories onto real teacher performance by returning to our observational data. Look at Mr. Smith's profile. He achieves perfect scores at the top of the chart for handling disruptions and effective time use. But trace his path to the bottom of the chart. His rating for cognitive activation drops to near 0. Translated to reality, Mr. Smith runs a highly disciplined classroom, but he relies on a transmissive style, where the class choruses answers, and the teacher consistently avoids any intellectual challenge. Switch focus to the blue line mapping Miss Jones. She achieves exceptionally high scores in the middle of the matrix regarding competent support and social relatedness. Yet, despite that warm environment, her trajectory also collapses in the third section. Miss Jones offers benevolent feedback, but she breaks tasks down so simply that she removes the productive struggle necessary for constructivist learning. These divergent profiles suggest that the 3 dimensions operate as independent axes. Scoring at the ceiling of management or emotional support doesn't naturally lead to high cognitive activation, and as we saw with Miss Jones, prioritizing a supportive environment can sometimes lead to simplifying the content until the cognitive challenge disappears. Profiling instruction is one thing, but the ultimate empirical test is whether these observations actually predict student learning outcomes. This yields the central paradox of the framework. It demonstrates robust observer reliability, yet its predictive validity is highly mixed. The theoretical expectation is clear. Classroom management and cognitive activation should strictly predict student achievement. But out of 10 reported effects for management in the literature, only 6 were statistically significant. For cognitive activation, only 3 out of 6 reported effects proved significant. Why does a theoretically sound framework produce such inconsistent empirical evidence? Educational research deals with intense methodological confounders, ranging from small sample sizes to the mathematical discrepancies between latent and manifest modeling. The most critical confounder responsible for these mixed results is the selection of pre- and post-tests. If a study uses identical achievement tests at time 1 and time 2, almost all variance in the final score is absorbed by the initial score. This leaves a tiny sliver of residual variance for teaching variables to target. When researchers use differently calibrated testing instruments, they reveal the large, significant effects predicted by the framework. This suggests the apparent lack of predictive power is often a statistical artifact. When the initial test scores absorb the vast majority of the variance, it leaves almost no room for the instructional quality to show its impact, even if the pedagogy itself is highly effective. The 3 basic dimensions framework is a powerful, parsimonious tool for the structural analysis of classroom instruction. But we have to question whether these 3 dimensions are truly exhaustive. Researchers frequently point to missing generic elements, arguing that a complete model must also measure content clarity and knowledge consolidation. There is also a valid challenge to the assumption that cognitive activation is a truly generic dimension applicable across all subjects. Assessing cognitive depth is impossible without simultaneously judging the mathematical or scientific correctness of the content being taught. To resolve these limitations and advance the field, researchers must standardize the operational subdimensions across future studies. Until standardization is achieved, frameworks like this remain brilliant analytical lenses. They give us the structure to describe the extreme complexity of instruction, even as they continue to challenge our ability to predict its ultimate impact.